Hi everyone, in today's video we are going to learn about multiprocessor architectures. Multiprocessor systems can be divided roughly based on memory organization, and it can be classified into two broad categories: shared memory and distributed memory architectures. So what are the basic ideas behind this classification? In shared memory multi-computers, the memory unit as a whole is shared by different processors in your computer, and they can again be classified into three categories: uniform memory access, UMA model, then you have non-uniform memory access, NUMA model, then you have a cache-only memory access, COMA model, right? Let me start our discussion with the multiprocessor architecture itself. As the name suggests, you can see in the diagram you have a number of processors out there in a single chip. Processor 1, processor 2, up to processor N. As there are multiple number of processors in a single CPU, this is called a multiprocessor architecture. Now, as you know, memory is necessary for any kind of computation. So, depending on how the memory is going to be used by different processors, these three classifications have been done. First, let me start with uniform memory access, UMA model. Just as a beginning, look at the statement. In this model, all the processors share the physical memory uniformly. All the processors have equal access time to all the memory hours. That means if you look into the diagram, you can see there are n number of processors and there are n number of memory elements. But these memory elements are independent of the processors, and they are connected to the processors through a interconnection network. This interconnection network has bus, crossbar, then multi-stage networks implemented in them, which we are going to study later on in this module, acts as a way of communication between different processors. Sometimes it might be necessary that different processors need to communicate in between themselves. So there must be a way out for that. And this interconnection network is the way out to do this communication. When all the processors have equal access to all the peripheral devices, the system is called a symmetric multiprocessor. It means that all the processors have equal priority to all the shared memory units as well as to all the peripherals. And then it will be called a symmetric multiprocessor. However, sometimes some processor might have a higher priority on a particular unit over the other processors. In that case, the system will be called an asymmetric multiprocessor, when only one or a few processors can access the peripheral devices, the system is called an asymmetric multiprocessor. So, in a nutshell, what was the idea behind uniform memory access? You have a shared memory space, and this shared memory space can be equally accessed by n different processors through a interconnection network. Now come to the next model, which is non-uniform memory access model or NUMA model. In NUMA multiprocessor model, what happens? The access time varies with the location of the memory word. In other words, the shared memory is physically distributed among all the processors, called local memory. The collection of all local memories forms a global address space which can be accessed by all the processors. Let we look into the points one by one. The shared memory is physically distributed among all the processors called local memories. Just look into this diagram. Here again you have n number of processors, and here is your memory unit. Now, in this case, if you look into the memory unit, you can find that for n processors, this global memory unit is split into n number of different memory units, and different memory units was assigned to a different processors to act as local memory to the particular processor. For example, if you look into the local memory 1, it is attached to processor 1 and it acts as a local memory to processor 1. Again, if you look into the memory segment local memory 2, you can find that it is acting as a local memory to processor 2 and so on. Now, at the end, what happens? The collection of all local memories forms a global address space which can be accessed by all the processors. Again, although the memories have been made local to the processors, it doesn't necessarily mean that a particular local memory can only be accessed by the processor to which it has been assigned. The memory units as a whole acts as a global memory space which can be accessed by any processor whenever necessary by this interconnection network. You can see again in this case, like UMA model, all the processors and memory units are connected to one another via this interconnection network. So this was the basic idea behind NUMA model. Now come to the third model, which is cache-only memory architecture, COMA model. Now, COMA model goes like it is actually a special case of NUMA model, and what happens here is all the distributed main memories. Just have a closer look at this star and give it a thought. All the distributed main memories are converted to cache memories. Now, what happens? You can see that somewhere here you have a global memory which can be accessed under uniform memory access model by all the processors. But along with that global memory, say you have a global memory here, global memory. Now this global memory is accessible by all the processors equally, but along with this global memory, you can notice that all the processors have their native cache attached to them. This is the idea behind this cache only memory access model. Here, actually, you have amalgamated this uniform memory access model and non-uniform memory access model into a single CPU. So this was basic classification and basic concept behind shared memory multi-computers. So why shared memory multi-computers? Because memory somehow is being shared by the different processors which are present into the CPU. Next comes the distributed memory multi-computers. Now, these are basically multi-computers. A distributed memory multi-computer system has multiple computers, and these multiple computers are known as nodes, which are interconnected by message passing network. Each node acts as an autonomous computer having a processor, a local memory, sometimes input-output devices. In this case, what happens? All the local memories are private and are accessible only to the local processor. So here is a diagram for this distributed memory multi-computers. Here you can see that here there are a number of multiprocessor processors. That means under each processor you have multiple number of processor embedded into them, and they are connected via a message passing interconnection network. Now all these units are actually independent of one another. That means whatever memory are there attached to them are native to a single processor. Some of the processors or some of the computers might have access to peripheral devices, input output units, but this entire thing will act like a single computer. So this was the idea behind distributed memory multi-computers. Now let me start to discuss shared memory architecture in detail. So what is the main feature of this shared memory architecture? All processors can directly access all memory locations in the system, as we have noticed during our previous discussion, thus providing a convenient mechanism for processors to communicate. So all the processors can access memory unit in the system directly, although all the processors are connected via interconnection network. So there is obviously a convenient mechanism available for the processor to communicate with one another. So there is location transparency, which you can clearly think in terms of cache-only memory access. Then abstraction is there. Abstraction supported in the sense as that on today's uniprocessor. That means user has the same feeling when a user uses uniprocessor systems. Memory usually is centrally placed because, as we have discussed, memory unit has some global address space, and memory unit can be accessed by all the processors centrally. An example. An example of this architecture is symmetric multiprocessor system. Now, just have a look into the diagram for the symmetric multiprocessor system. In symmetric multiprocessor system, what happens? You can see that there are a number of processors indicated with P in this diagram. Then you have a shared bus or interconnection network. Then you have a single piece of global memory space. Then you have input-output peripherals. Now, what goes on here? These different processors have equal access to the memory uniformly through the shared bus and to the peripherals, as we have told about location transparency. To justify that, just look at this dollar signs along with all the processors. These are actually cache memories local to the individual processor. So here you have location transparency. That means the computation, what will go into the first processor, and the data related to that computation for the time being will be stored into the location native to this particular processor. That means into its native cache. And this will be same for all the processors, although the main memory unit acts as a global memory address space. However, this presence of local caches introduces an interesting problem called cache coherence problem in shared memory architecture. So, how this happens? Just first look into the statement. The use of large multi-level caches can substantially reduce memory bandwidth demand of a processor. Why memory bandwidth demand? If the CPU has no local caches attached to them, then what will happen? For each computation, the processor has to access this global memory space. That means the bandwidth of this shared bus or bandwidth, this bandwidth in this channel need to be much larger because there will be frequent request for memory access which it needs to compensate. So native caches actually substantially reduce that memory bandwidth demand of a processor, because now what will happen? Whatever computation this processor needs to do, the relevant data will be stored into this local cache. So no need to frequently access this global memory. Now, this also introduced a peculiar problem called cache coherence. So how does it look like? It looks like, say, here you have processor A and here you have processor B. Now, Here is the local cache C1 attached to processor A, and here is the local cache CB which has been attached to the processor B, and these are, and here you have your global memory space. Global memory space. Now what happens? Say processor A requires some data X, which is now N, from to the global memory space. Now here we will have a compulsory miss because the item is not into the cache. So now value N has been introduced into memory location X into cache A. Now after some time, what happens? Say processor B requires the same piece of data, that is this N. So it will read N into its local cache, and now time goes on. After some time, the next instance, what happens? The value of N, value of X has been updated by processor X, and the new value of X is now N minus 1. If your memory writing policy is write through, then what will happen? At the same time, when the data item has been updated into the cache, it will be updated into the main memory also. Now in main memory or general purpose main memory, the X has a new value N minus 1. If you look carefully into the entire situation, what happens? Now cache A or processor A has access to the latest value of X, as well as latest value of X is available into the general purpose main memory also. However, if after some time B requires the same piece of information, it is not going to look into the general purpose main memory for this item X. Why? Because at that time there will be a cache hit, because this X data is already available into the cache local to processor B. But the problem is the data in processor B is an old one. The value of X has not been updated into the cache CB, although it has been updated into the general purpose main memory. So you can see that the data here are not coherent, right? As well as some kind of inconsistency occurred here. Because of this, multiple caches, multi-layer caches. So this is the basic idea behind cache coherence problem, and the inconsistency arised due to it. At the next lecture, we will study about how to solve this cache coherence problem and solve the inconsistency which has been arised due to it. And as a last point, I will like to draw your attention to a thing called cache writing policy. As you have noticed in this example, when an item has been updated into the cache, it needs to be updated into the main memory because the actual place for data is main memory, from where different processors will access that particular data. So whenever a processor updates or writes to some data, it is first updated into the cache. After some time, at some point of time, you need to update the same piece of information into the main memory so that all the processors get the updated information from the general purpose main memory. To do this, actually, there are two policies. One is write to update policy, another one is write back update policy. And how do they go? In case of write through mode, data is written in cache and in source memory at the same time when it is modified. No matter how many times data is being modified in cache memory. On the other hand, in write back policy, what happens? Data is written only into the cache and it will be updated into the main memory only when the data will be replaced from the cache. Just look into this diagram. This is your write through policy. Initially, the value of x was 0, which has been required by the processor here, right? So this x equals to 0 value has been introduced into the cache. Now, after computation, after computational execution, this processor P1 does what? It updates the value of x to 5, and this updated value is written into the cache. You can see that it is updated here. Now, when the processor is updating the value of cache, at the same time, this value will be updated into the general purpose global memory space also at the same time. But in write back policy, what will happen? Initially x is 0 and this x equals to 0 has been introduced into cache by processor P2 and it has been updated to 5 into the cache, but it will not get updated into the main memory. Until when? Until it gets replaced by some other data. When it is replaced, say this is being replaced by some other data, then this will be updated into the main memory. This is the write back policy. So this was the idea behind write to and write back policies. Now have a look at the informal definition of cache coherence. It goes like a memory system is coherent if any read of data item returns the most recently written value of that data item. Just give this definition a thought. I highlight the most important portion. Most recently written value of that data item must be accessible by the processor. And if most recently written value of the data item is accessible, then the memory system will be called coherent. Just like our previous example, have a look into this example. Here you have two processors, processor 1, processor 2, and into the shared memory, a data item X is there. Now, at the beginning, processor P1 accessed this data item and it is loaded into its native cache. After some time, say at time instance t plus 1, processor P2 read the same data. So until now, we have no cache coherence problem here because all the processors have access to most recent data item or most recently updated data item, if I say precisely. Then at time instance T3, say what happens? Processor P1 updates the value of X data item to X1. And if your memory writing system is write through, it will be at the same time updated into the shared memory also. And this everything happens here in time slot T3. After some time, say at time instance T4, what happens? Processor P2 now again makes a request for the data item X. Now what will happen? This data item will be found into its native cache. That means now here you have a cache hit. So as there is a cache hit, no need to look into the shared memory. Just go as per the definition of cache hit, go on with computation with the data which is available into your cache. But here the processor have no access to the most recently updated data item. So the situation is not coherent or memory access is not coherent. You need to develop some mechanism to solve this situation. So just have a deeper look into the definition. A memory system is coherent if read after write works for a single processor. In other words, if CPU A writes N to location X, all future reads of location X must return this N, as this N is the most recently updated data into this memory location X. Right? Now, if some processor has access some other value than N for this memory location X, then the situation is not coherent. Now, consistency. What is consistency? This indicates when a modification to a memory is seen by other processors. Clearly, this is not be instantaneous. Just how the situation is inconsistent here, just have a deeper look into that fact. Where is the diagram? Yes, here's it. Now, this updated data item x1 is not visible to P2 due to the entire architecture. So this is not consistent. This is consistency problem. You need to develop some mechanism to solve this coherency and consistency problems, which we will study during the next video. Till then, just go through the reading material until this point carefully and give them your thought. Thank you.